Okay, so I mentioned this one was actually written almost trying to be a little bit obnoxious, just to show how when you get something like this, I mean, well, you're not going to solve this with the power rule, right? It's not a power function. It's a whole bunch of things thrown together. Now, you also are not going to get the answer by trial and error. Uh, or if you do get the answer by trial and error, you've probably already had some experience at this, and you also know how to find it not using trial by error. But typically, most people aren't just going to look at this and guess the right answer. So you have to apply a strategy that allows us to apply the properties of antiderivatives, and by that I mean these three properties here. Uh, Pulling out scalar multiples, breaking them up over sums and subtractions. That's really what you're going to want to do. Just keep breaking this down until it's manageable. So start with the most obvious thing you could do. And by obvious, I mean at the outermost layer of complexity. You've got a function plus another function. Well, we're allowed to break that up into the sum of two antiderivatives. So I get the antiderivative of 4 sine of x plus the antiderivative of 2x to the fifth minus the square root of x all over x. So that's the first step, is just to break them up into the sum of two antiderivatives. And neither one of those on their own is a joke either. They're still going to have to, still have to do a little bit of work. But we can deal with them. Let's do two things. On the next step, for this first antiderivative, let's take this 4. This is a constant multiple, right? I can take where is it? I can take this one with k equal to 4, and I can pull it out of the antiderivative. That's what this property says. So I can take this 4 out, and I can go 4 times the antiderivative of sine of x. And in the next one, I'm going to just split this fraction up again, just like we did in the previous example. So write this as 2x to the 5 over x minus the square root of x over x. And then there we go. Now we can deal with those. So what about sine of x? What is the antiderivative of sine of x, by the way? If I was just solving this problem, well, what would it be? Cosine? Well, the derivative of sine of x is cosine. So maybe, what about the antiderivative? Maybe it's cosine as well. And remember, if you're ever unsure, just write it down so that you have it right in front of you. Then you can stop thinking about it, and then you can just focus on testing whether it works. What happens if you take the derivative of cosine of x? Well, you actually get negative sine, which is not what you want. You want positive sine. So the fix is to put a negative sign in front. Right? So that now you can test that the antiderivative of sine is negative cosine, because if you took the derivative of negative cosine, would you get sine? And the answer is yes, because if I differentiate cosine, I get negative sine, and then this extra negative turns it positive, so that's what you want. And then, of course, I would have a constant of integration if this were the antiderivative I was trying to find. But that's not the one we're trying to find. We're actually trying to find this one. So I'll just draw a line just to separate the rough work. So that means this antiderivative of sine of x is actually going to be 4 times, we'll have the 4 will be there, and then we'll have negative cosine of x. And I'm not going to, this constant of integration, I'm not going to copy that down over here because there's still another antiderivative to worry about over here. So until I've actually evaluated all of the antiderivatives, I'm not going to write my constant of integration. So here, let's deal with what happens in here. 2x to the fifth divided by x, well, that's going to give you 2x to the 4. And what about the square root of x over x? Well, that's going to be, remember, I think we've done one like this before, but I'll just do it anyway. Root x over x, that's x to the 1/2 over x to the 1, right? Convert them both to exponents, and then you can actually reduce it by applying properties of exponents. I've got x to the 1/2 minus 1, and 1/2 minus 1 is negative 1/2. So I'm going to have x to the negative 1/2. So this will be minus x to the minus 1 over 2. Okay, now I can't pull that 2 out yet. If your instincts are saying to take this 2 and pull it out next, you can't, because this 2 would need to be multiplied onto everything in order to do that, right? This property that I'm kind of referencing right now. I can pull scalar multiples out, but they have to be multiplied onto the entire rest of the integrand. That's what this is referred to, by the way. And maybe I'll actually, that's a good thing to add. I forgot to add that. I'm going to go back to the first page and add a little comment here. When we write down things like this, I know this is a bit of I'm interrupting myself here. But this is referred to as the integrand. This is just terminology. It's handy to be able to use. So I'm talking about this piece here. The thing that you're actually trying to find the antiderivative of is referred to as the integrand. Okay, so maybe you want to add that to your notes as well. Okay, where was I? Yeah, so if we were applying this property here, this must be multiplied onto everything else. But in our case, it's not. The 2 is only multiplied onto the x to the 4. But the good news is we can still deal with this, but we have to split it up first. So I'm just going to rewrite this as negative 4 cosine of x, and then say this is plus 2x to the 4 with respect to x, in the antiderivative of 2x to the 4 with respect to x, minus the antiderivative of x to the minus 1/2 with respect to x. So I have to split that up using the subtraction property. So I'm using property 3 here, where this was 2x to the 4 and this is x to the negative 1/2, and I'm splitting it up into 2 different antiderivatives of subtraction in the middle. And then now I can pull the 2 out because it is multiplied onto everything else. So I get negative 4 cosine of x plus 2 times the antiderivative of x to the 4 with respect to x, and this one, we're actually ready to evaluate this because this is just a power function, x to the minus 1/2. This is one we already actually worked out on the previous one, right? Actually, we have it still on this page. We had the antiderivative of x to the negative 1/2, and we got, using the power rule, we got x to the 1/2 divided by 1/2, because negative 1/2 plus 1 is 1/2. So we're going to do the same thing here. So this is going to be minus x to the 1/2 divided by 1/2. And notice again, I'm not putting the plus c yet. And the reason for that is because we still have one antiderivative left to evaluate. So on the next step, which I can write down here, I'll have negative 4 cos of x plus, okay, now we'll do the power rule on x to the 4. So I'll get 2 times x to the 5 over 5. Then let's clean this up a little bit. This is, I can write this as minus 2 x to the 1/2, because that's what dividing by 1/2 is the same as multiplying by 2. So now we've finished finding the antiderivative. There's no antiderivative symbols left, so now we can write our constant of integration. And that's how you can finish that example. Okay, so I think that's the end of the section, and I'll stop there. So that's the idea of the antiderivative of a function. Next section will be really just paving the way for an application of why you would care about this. Because that might be something you ask. Remember, the derivative gives you something geometrically. If you take the derivative of a function at a point, it gives you the slope of the tangent line at the corresponding point on the graph. Well, what does the antiderivative get you? That is not clear yet. And the next section is where we will develop the tools we need to actually formulate what it is exactly that the antiderivative gets you. Okay, so I will stop this here.